Hello, welcome to the 8th lecture, the Virial equation of state. Other than van der Waals equation, several other equations have been proposed from time to time to account for the pressure, volume, temperature behavior of real gases. A good equation of state should be simple to present. It can express the pressure, volume, temperature behavior under moderate ranges of pressure and temperature, and it should use only a few adjustable constants or parameters. A brief description of one more equation of state called the Virial equation of state is given in this lecture. It is the most general equation of state proposed by Kamerlingh. He expressed the product P into PVM as a power series in 1 by Vm. Hence, the equation of state becomes PVM, Vm is the molar volume, equal to RT into 1 plus V of T by Vm plus C of T by Vm square plus etc. Where Vm, as I said, is the molar volume, V of T and C of T etc. are the temperature dependent second, third, etc. Virial coefficients respectively. The first Virial coefficient evidently equal to RT. The term B represents the contribution to deviations from ideal behavior arising from interaction of a pair of molecules. C represents interaction from triplets of molecules. D, E, etc. represents interaction between 4, 5, etc. molecules at a time. Practically, the equation is rarely extended beyond the term containing C. In general, the coefficient of B is negative at moderately low temperatures, becomes 0 and then positive as the temperature is raised. The temperature at which the second Virial coefficient B is 0 for a gas is called its boil temperature. At this temperature, while the second Virial coefficient vanishes, the higher ones become insignificant so that PVM becomes equal to RT, which is the equation for an ideal gas. The Virial equations can also be expressed as a power series in pressure by this equation. That is, we are changing the 1 by Vm square, 1 by Vm cube, etc. in pressure, as PV is a constant. Here, A2, A3, etc. are new temperature dependent Virial coefficients. And there are also some significance for these Virial coefficients is that at low pressures, the first Virial coefficient equal to RT. First Virial coefficient increases with increase in temperature. The second Virial coefficient, as I already said, is negative at low temperatures, becomes 0 at a particular temperature, and then increases as the temperature increases. The temperature at which the second Virial coefficient is 0 is the boil temperature. Next, we have to express the van der Waals equation in Virial form in order to find out an expression for boil temperature in terms of van der Waals constant. It is an important derivation. So now you take your textbook or any paper and derive it. Try it with me. We know for 1 mole of a gas, the van der Waals equation is P plus A by V square into V minus B equal to RT. Here we can rearrange it as P equal to RT by V minus B minus A by V square. From this equation we can rearrange and write it as this, and if we are taking a 1 by V outside, we will get another equation P equal to 1 by V into RT by 1 minus B by V minus A by V. Then what will be the PV? Equal to RT into 1 minus B by V raised to minus 1 minus A by V. We know an equation 1 minus x raised to minus 1. So theorem 1 minus x raised to minus 1 means 1 plus x square plus x cube plus etc. You may be studied it in your degree classes or plus 2. It's a theorem that is 1 minus x raised to minus 1 equal to 1 plus x square etc. Like that, I am expanding this term also as 1 plus b by v plus v square by v square plus etc. And combining with the former equation will become PV equal to RT into, in place of 1 minus b by v the all raised to minus 1, I am giving this expansion and the new equation becomes this. Next, how it converts to this type, that is, I am extending the bracket, or I am involving this term also inside the bracket. For that, I want to multiply and divide this term with RT. Then we can take an RT common from these two equations. So this equation, there will be an RT in the denominator. You got it? That is for taking this A by V inside the bracket. It's possible that if you divide this term with an RT, then it will compensate it. That is P equal to RT into 1 plus B by V minus A by V RT plus V square by V square plus etc. You see, for this V, the two terms, the V is common, so we can take the 1 by V outside and the equation becomes PV equal to RT into 1 plus 1 by V into B minus A by RT plus 1 by V square into B square plus 1 by V cube into B cube plus etc. This is the van der Waals equation in Virial form that we have seen in the first slide, that PV equal to RT into 1 plus capital B by V plus capital C by V square plus capital D by V cube plus etc. as Virial equation. Here for capital B it is B minus A by RT, and then for capital C, the third Virial coefficient, we have van der Waals constant B square. By that we derived an equation, van der Waals equation in Virial form. From this equation, the second Virial coefficient B equal to B minus A by RT. Now, you can say at boil temperature, we know what's happening at boil temperature. Temperature at which second Virial coefficient vanishes is called the boil temperature. That is, at boil temperature, B, the second Virial coefficient, automatically becomes 0. That is B minus A by RTB. That is, at boil temperature, T equal to TB. So, boil temperature, just I am changing the temperature as boil temperature. B minus A by RT equal to 0. Then, B equal to A by RT. That is, TB equal to A by RB. That is, this is an important equation which is we have derived the boil temperature in terms of van der Waals constant by using Virial equation of state. By this concept, Virial equation is very important, and we do not get any expression for boil temperature if you don't have a Virial equation. By this is very important. You must study this derivation and the expression for boil temperature also. And by this, I am concluding this lecture. Thank you, dear students.